Welcome to Calculus Chat, a weekly discussion with your lecturers for 114. I'm Dr. Biggs, and here with me is Dr. Kellerman.
Hello.
And Professor van der Walt.
Hello.
So, we are now well and truly coming towards the last stretches of this module, but I would say there are still quite a few beautiful and exciting things to be done before we reach that finish line.
Yes, absolutely. And in the lectures that were posted for this past week, we had L'Hopital's rule and curve sketching.
Yeah, no, both quite beautiful. And I mean, L'Hopital's rule is it's actually in some ways it's quite astounding. When you've been struggling with some limits and you have all kinds of special little tricks that you pull off, and then you're like, here's an algorithm that solves many of these problems, quite straightforward. And all I need to do is put it through my differentiation machine.
Yeah, just make sure you don't put something in there that doesn't belong there.
Indeed, it is not the cure for all ills. And I guess the danger with L'Hopital's rule is it's so powerful that you're tempted to think you can use it everywhere, but you can't. And there's also a beautiful bit of history to L'Hopital's rule, or shall we say some controversy also, yeah.
Yes, L'Hopital is actually not the inventor of the rule named after him.
Most historians would say so, yeah. But I mean, at the time, there was a big arguments about, well, who exactly invented it? Because as I understood it, L'Hopital was paid one of the Bernoulli brothers, and he was a student of one of the Bernoullis.
Stole his supervisor's result.
From what I understand, he had an agreement with this particular Bernoulli that he could use this Bernoulli brothers' results in the book that he was writing.
Aha.
But it's not clear to me if he had bad intentions, because in his book he did, in the preface, credit the Bernoullis and Leibniz for some of the results.
I see.
I think as the book became very famous and L'Hopital became very famous, then
Bernoulli was like, no, that is my fame. I need to show that I'm better than my brother.
Yes, I mean, this one should interpret this against the intense rivalry between the Bernoulli brothers themselves.
In fact, the Bernoullis were several generations of accomplished mathematicians, so it's worth remembering that there's not just one Bernoulli. When you keep seeing the name Bernoulli in maths and physics and statistics, there were actually several Bernoullis. They were a very mathematically prolific family.
Yeah.
They were like what the Bachs were to classical music, the Bernoullis were to mathematics.
Mm-hmm.
Although the situation reminds me, in group theory there's a theorem called Burnside's lemma, which wasn't actually discovered by Burnside. It was popularized by Burnside. It was actually discovered by Frobenius. And one of the standard names by which Burnside's lemma is known is the lemma not by Burnside. So you'll sometimes see it called the lemma not by Burnside. So one could perhaps speak of the rule not by L'Hopital.
Yeah, I mean, in the end, what's behind a naming convention?
Yes. Well, I mean, in this case, I don't think it's particularly important because all parties concerned have no more interest in who the theorem is named after. But one should, I think, in principle, give credit where credit is due as accurately as you can.
Yes.
But there's a funny story. I think it was Kakutani, he's a famous Japanese-American mathematician, did a lot of important work in analysis. And among others, I think he proved a fixed point theorem for set-valued maps. This theorem had enormous implications in mathematical economics. For instance, this John Nash won the Nobel Prize in Economics for work he had done in game theory. And his result in game theory is an application of Kakutani's fixed point theorem. And then in some lecture, Kakutani was sitting at a conference, the speaker kept referring to this Kakutani theorem that he's using. And then Kakutani asked, well, what theorem is this? He'd forgotten his own theorem.
Yes, I've wondered at what stage is a result named after a mathematician? At what stage does it become known as Smith's theorem?
I guess when it turns out to be a very important theorem.
Well, I would guess it's a sort of an organic thing that everybody starts referring to, that paper by Smith, that theorem, and then that evolves into Smith's theorem.
Yes, I guess so. There are other things in mathematics where mathematical objects are named for persons in the same way that we would name a street after somebody.
Yeah.
So, for instance, Banach spaces are called Banach spaces in order of Banach, who did a lot of important work in the field, and similar with Hilbert spaces and things like that.
Yeah, no. So it's, I mean, in a way, it's like many names, it's sort of a reflection of the culture. And I guess things can get heated, like, for instance, they did with
Ah,
Leibniz and Newton, when you have two different countries wanting to claim the honor for themselves.
So, and I think in astronomy, if an astronomer discovers an asteroid, they can pick its name. But this is not the case in mathematics. The mathematician can't name a theorem after themselves.
no, they can't. I have an interesting story about a mathematician who I've actually briefly met once, who was it's a Bulgarian mathematician who did a lot of important work in what is known as interval analysis. And in there, there's a concept of continuity, which he called S continuity, S being for segment,
Hmm.
although his surname being Sendoff. This fortuitously for him later evolved into Sendoff continuity.
Aha.
So the lowercase s for segment just kind of morphed into an uppercase S for Sendoff.
I see, I see. So the plan for me is I should make a big theorem or a big
A big
space.
space. Yes. And then at some point, somebody just adds another G.
Okay, so that was quite a tangent that we started from L'Hopital's rule. The other thing you mentioned we did was curve sketching, and for me, this is quite a beautiful area in this course, because you sort of start bringing together everything we've done so far, and you have to understand everything and put it together for one project to actually sketch this curve and use all your
Mm.
tools together.
Yes, I think one of the students actually mentioned this on Discord. That curve sketching problem is basically all of 114 in one problem.
Exactly.
Which, and to a good extent, it is because it goes way back to the beginning of the course. Finding the domain, solving an inequality. It really is almost everything just about everything we've done up to now, all in one problem. It's great.
Okay, and then in TUTS, we also tackled some good problems. Um, the one problem that I quite enjoyed was the one where you have to use Rolle's theorem to prove that equation has at most one root, and this sort of comes to the idea of a proof by contradiction. And I don't know how many of our students have seen this idea, but it's a really powerful idea in mathematics, and we use it all the time. If we want to prove some statement, then how we sometimes can go about doing that is to assume that the statement is not true, show that that leads to complete nonsense, something like 1 equals 2, and then we can say, well, clearly it cannot be not true, because if it was not true, then you'd have nonsense. So therefore, it must be true. And it's sort of logically, the first time you encounter that, it's a little something to wrap your mind around. But a few years into maths, this is the one of the most natural ways you go about proving something.
Yeah.
It is, but I always prefer to avoid contradictions where possible. I once read an interview with a famous mathematician who claimed that he described proofs by contradiction as being in Never Never Land. The moment you assume something that you actually know to be false, then you're in a mathematical fantasy world and it's something best avoided if possible. And he claimed that if you restructure the argument correctly, you can always prove something without using proof by contradiction.
Hmm?
I don't know if that's true, but where possible, one should try and avoid contradictions unless it's the most elegant tool for the job at hand, which I think the problem that you're referring to with Raleigh's theorem, proof by contradiction, is certainly the most elegant tool. But then the other extreme is what I've seen sometimes happen, for example, in axiomatic geometry, is people get so used to proving things by contradiction that they almost start every single proof with assuming the opposite of what they're supposed to prove, and oftentimes it's not actually necessary.
And especially when you, I think for me, when you're starting to deal with existence claims, if you prove that something exists by making a contradiction, it's not very satisfying. I would much rather have a proof that constructs the
Mm.
object that I want and actually tells you how to get to the thing you want in your theorem, rather than just saying, well, it must be because. Rather, it often for me, a proof by contradiction doesn't give, you don't learn that much about the depths of the problem and how you can solve issues of
Mm.
approximation or something in the problem sometimes.
Yeah, well, I would often start out, trying to do something directly, and then I would say, okay, well, let's assume it doesn't work, kind of a thought experiment, and then do a proof by
Mm-hmm.
contradiction, and then reverse engineer that to see what the direct proof would look like.
Yeah.
I know there are constructivist mathematicians who have a big issue with proof by contradiction.
Yeah, but without it, so I mean, we would lose branches of mathematics, which sort of use it at quite fundamental levels.
Yes. Well, I mean, there is a connection at the level of mathematical logic, a connection which I do not entirely understand between proof by contradiction and the axiom of choice.
Hmm.
And I'm afraid if you throw out the axiom of choice, then that's a bit of a problem for me as a mathematician. I mean,
My life's work, toodle doo.
although a senior mathematician, somebody who by now has been officially retired for several years but is still very active in mathematics, once told me that the older he gets, the more worried he is that, when he dies and he reaches the pearly gates and Peter is going to ask him if he used the axiom of choice or not.
Oh, joy.
Yet another tangent.
Talk about taking your mathematics seriously.
Yeah. Yeah, but I mean, in the tutorials, I think we've now also come to the point where when we're discussing a problem, we more or less just outline sort of the structure of the thing, how to go about doing this, and leave all the computations to the students. Because, I mean,
Yeah.
you know, well, okay, so, well, what would you do? Okay, well, you would differentiate. You know how to do that. And you would set it to zero and solve the equation. You know how to do that. And then,
No, I mean, this is exactly the symptom of what we were discussing earlier. We've been building so much
hmm,
tools and we can now rely on those tools. So now, especially at this stage, it's no longer about actually the details of the argument. We covered that weeks ago. Each part of the argument, right? We know how to do, you know how to do, we've tested you, you've studied it.
hmm,
The things that we are doing now is sort of looking at a higher level. How do we bring different parts of everything together? And I mean, curve sketching is a beautiful example of that, right? It's no longer about knowing what the derivative is or even the first derivative test or increasing or decreasing, proving that from scratch. It's bringing all this knowledge together.
yeah. And I mean, that's a important part of the learning process is integrating knowledge. So you've done this, and you've done this, and you've done this, but can you bring it all together?
Exactly. And I mean, for me, that's the most interesting and possibly the most challenging part of learning something new is being able to understand it well enough that you can pull all those nodes together and you understand how the different things you've learned are interconnected. Okay. And we still have a little bit to go before we finish off with theme four, another two lectures with another beautiful application, which is optimization.
Yes, we'll be discussing some simple so-called real-world applications of calculus. You're finding what essentially asking what is the best possible way of doing this, whatever that is.
I don't know if this one's covered in your lectures, but one of the examples I really enjoy doing in first year is the optimal dimensions for a can. If you want to minimize the surface area, which is to minimize the amount of material you need to make a certain volume.
Yes, that's in fact one of the examples in the lectures, and it's quite a nice example. Shows you how you can use this kind of thing in really kind of practical ways.
Of course, I mean that problem will have a few other constraints about it in the real world, but that is a fantastic first thing to know in terms of a design. And it's for me amazing how just with this simple first year level calculus, you can already start doing some very serious problems and learn a lot about things you want to design.
Absolutely. Of course, the most difficult part of doing these kinds of problems, and this is true both for the kind of toy problems that we do in the course, and in terms of the actual real world application. So if you were to go out into the world and try and solve a problem, the most difficult bit is the modeling, which is the
Yes.
first step. It's because you're getting a bunch of information which is not in mathematical form,
Yeah.
you know. Some person just comes to you and say, I want to do this, this, and this, and this, and that, and he usually doesn't even know what information you need.
Hmm.
And it's up to you to get the right information and then to translate that information into a mathematical problem and the correct mathematical problem.
And what is also often done is to make assumptions that simplify the model so that it can at least be solved, but the
Yes.
assumptions have to be reasonable. And one sees, for example, with financial models, oftentimes in extreme cases, the model does not predict the market because the assumptions that underlie the model simply aren't equipped to handle extreme scenarios. And one must
Mm.
acknowledge if the model is faulty and not try and suggest that the fault lies with the thing that is being modeled, which is, I think, a sin that mathematicians are sometimes guilty of.
Indeed.
My theorems are fine. It's your problem that's wrong.
Well, I very much also think it's this sort of some mathematics is great, but some people start to put it on too high a pedestal. They think that it is you can solve everything. You just need to make your mathematics complicated enough, and it will solve it. But there are some things that fundamentally, without making some assumptions, you just can't mathematically deal with it. Maybe in I don't know 100 years, 1,000 years, we'll develop a new branch of mathematics that can deal with it better. But there will always be problems that if right if all we have is a hammer, then we start seeing everything as nails.
Yeah.
But that's not the only tool in that works for everything.
Yes, I saw this last year with the COVID pandemic. You had these cases where I guess you could call them COVID denialists or COVID revisionists would say, well, the epidemiologists said that there would be so many deaths and there weren't so many deaths. So that proves that this isn't really as big a deal as was said. But the point is, it's the model was wrong. It's not the phenomenon that isn't real. Or I've
Yeah.
also seen it with global warming, where they say, well, the model said that you'd have this kind of temperature increase, and we haven't had this kind of temperature increase, so that proves that global warming isn't real. But in fact, it's the model that's faulty. It's not that the phenomenon isn't real.
Yeah, or that the model simply isn't applicable in the way that we thought it was. I mean,
Mm.
r- really, for me, mathematics boils down to implications. If something, then something else.
Yes.
And well, if you don't meet that assumption, well, then clearly you can't say anything.
Yeah. Well, I mean, there are people in our own department who part of their research involves comparing different models for the same thing.
Hmm.
They can find out which models actually work based under which circumstances.
Indeed.
So this is a tough problem. Modeling is difficult, and it is as much an art as a science.
Yeah, and I mean, especially if you involve something in your model which is not deterministic, right? Like financial models, I cannot even imagine how you deal with the human component,
Well, they don't.
right? You have to make some serious assumptions about how humans act.
Yes, the assumption is that we act rationally. It's a big assumption.
Yeah, no, that's a problematic assumption, I would
Yeah.
say.
Well, that is the big problem with using mathematics in modeling kind of sociological things like
Mhm.
economics, which depends on human behavior, because the underlying assumption is that we act rationally according to certain criteria.
Yeah, I mean, it can be a useful tool for sort of developing your understanding of that system, but you have to understand that the tool has limitations. It's not going to solve everything and give you all the answers like some or other magical thing. Wow, beautiful stuff on optimization, right? And so in our course, we really only doing optimization, right, for one variable. Single variable calculus is what we're doing. We can sort of stretch it a little bit when we have like a two-dimensional problem, but a constraint, which we can then bring it back down to a one-dimensional question problem. But of course, as you go further in mathematics, it might be interesting. And certainly by second year, you will be dealing with multivariable calculus. And how do you optimize in that context?
Mm.
And then if you really stick to it, even further than that, then you can go infinite dimensional in a sense. That is, you don't have just a number of variables that you are trying to optimize over, but you sort of have something like, well, you want to find the best path. And you can move any bit of that path, a circle, square, whatever. You have sort of an infinite dimensional aspect to optimization there.
Yeah. Among all possible paths between these 2 points sitting on this surface, which one is best in whatever respect? Yeah,
Indeed.
that's a nice problem.
Not an easy problem, though.
Well, that's why we can have fun with it.
No. Well, I mean, the easy problems are usually not the funnest ones.
Now, there's the saying, problems worthy of attack prove their worth by fighting back.
Yes.
Beautiful. Okay, and well, with that, we will finish off our theme 4 and we will get started with our very final theme, theme 5 on integration. Right, so we're going to sort of start with a slightly different problem than we've been looking at for now, well, 2 themes, right? Rather than looking at, well, what is the tangent line, the slope of the tangent line to a curve, we want to ask the question, which seems quite different, about, well, what is the area under the curve? And like we did with integration, we're going to start really from scratch. How can we define this? How can we make a nice calculation for this?
Yes, this is really one of my favorite bits of mathematics. Is this integration theory? I think it's one of the places where I fell in love with mathematics
Mm-hmm.
because I did what is these days called alpha mathematics. I think in high school, meaning I did a lot of calculus in high school already in my grade 12 year, and then I just fell in love with this idea that, oh, you can calculate these surface areas. And then we did volumes of bodies of revolution, which is also an integration problem.
Oh, yeah, that is beautiful.
That's beautiful. And then I looked at this and I thought, this is so fantastic. I mean, I can calculate volumes of anything, of solid bodies. And I started deriving formulas for all sorts of shapes and pyramids and cones and everything I could think of using integration.
Yes.
Um, that was really fantastic. So I hope our students will enjoy it as well.
Yeah, no, there's a lot of fun to be had if you pay a little bit of attention and really get at how I think this is sort of the last, but another beautiful example for how we can build out of things you already know a new theory, right? We're not going to tell you something which is unjustifiable or that you could not do with all the tools you have already.
Mm.
We're just going to say, okay, well, we have a new problem. We want to calculate the area under the curve. What is a sensible way to start even attacking this problem? And then we'll slowly, over a lecture or two, build up a definition for an integral. And if you pay attention, it's like, oh, this is actually quite natural in a sense, almost to the feeling like I could have done that. And you might challenge yourself. Well, what if you change something? How does that change the definition? Right? And there's beautiful things to be played with here, I think.
So I think mathematics, to some extent, is about being in the right place at the right time. I also sometimes think, well, if I'd lived in the 1600s and I was contemplating calculating the area under a curve, I might also have done something like this. But it's been discovered already, so
Too bad.
And yeah, so then we will have the integral, and the amazing thing, one of the I mean celebrated results, is the fact that this is in fact related to our work on differentiation, and this is an aspect that we are certainly going to explore a bit, and that is, I mean, for me, if you just think about what are the 2 problems that you are asking, like the slope of a tangent line and the area under a curve, really, these things should not be related to one another at all. But amazingly, there is a beautiful, strong connection between solving those 2 problems.
Yes. That's one of the big miracles of mathematics is this result that relates integration to differentiation. Of course, while these two things are very closely related, when it comes to actual computations, integration turns out to be a bit more difficult than differentiation.
Yeah, no, I mean, differentiation, we've seen it now. We've built our little toolbox, and it can be really done quite algorithmically, right? As long as we restrict ourselves to combinations of our elementary functions, we can plug it into our machine, we crank it, and it spits out the derivative. And this is reliable and it does it. Whereas integration is sort of a bit of a different ballgame. It's much more open ended. You're given a function, any combination of our elementary functions, it's not so easy to actually find the area under the curve, and it could go beyond the mathematics, so it's much more, I would say, almost becomes more of an art than an algorithm. You have to think and be creative about how to solve the problem.
Yes, I've seen at some American universities they have integration bees, where basically competitions where they give integrals, all kinds of integrals, and students have to solve them like a spelling
Yeah.
bee, but it's involving integrals.
And I mean, we'll see. There are techniques of like certain patterns that you can get. And I mean, if you are running a computer program and ask it to try and find an integral, it tries to identify it. And I mean, I think even in the textbook, there's probably a list of standard integrals, but it's nowhere near as algorithmic. And it's so easy to step outside of any of the standard forms that are known for how to integrate it. But we will return to this topic certainly in a future calculus chat once we get further into integration.
Yes, integration is, I think, in part skill and part art, and there are definitely some clever tricks that you sometimes have to use.
Yeah, I mean, there are a whole chapter, several sections. I think there's a whole chapter in the textbook dedicated just to techniques of integration, which tells you it's not something that can be summed up in a page.
The students have been doing integration without it being called integration in several of our worksheets. They've had questions where they're given a derivative and asked to find the function that gives rise to that derivative. So the ones who did alpha maths in school might recognize this as integration, and the ones who didn't do alpha maths in school might not recognize this as integration, but they've already had some exposure to it.
Yeah, and I mean that comes to the heart of this beautiful result that we were alluding to. The fundamental theorem of calculus is tying the idea of integration, finding the area under the curve, to the idea of differentiation, or its reverse, anti-derivatives.
Yes, it's not often in maths that a theorem is called the fundamental theorem of such and such. So might be a contender for most important theorem in mathematics. Calculus is such an important field, and you have the fundamental theorem of calculus.
Yeah, I would certainly say it is a contender.
Yep.
So, beautiful things lie ahead in Theme 5. Lots of discoveries and fun still to be had. And I'm sure we will return to some of these topics again. But for now, that is it. And all the best with your week.
Bye.
Goodbye.
Ciao.